Embedded devices are all around us and require the ability to communicate between modules, FPGAs, and processors within a wide array of consumer and industrial electronics. The most common sources and types of problems when using low-speed serial data in an embedded application include timing, signal quality, and the data itself. To begin with, let's examine our embedded device's signal quality. Monitoring and improving quality of low-speed serial signals is a critical part of the debugging process. Currently what we're looking at is a clock signal that's causing us some problems on an embedded device. And what we want to do is identify possibly what's causing our communication problems. So to start off with, we're just simply visualizing the clock signal. But let's start off with looking at rise time. Ideally, this signal should have about a 2.4, 2.6 nanosecond rise time. So to do this, I'm actually going to first zoom in on our signal, and then I'm going to go into our measurement menu and turn on our measurements. I'm going to select rise time. And then what we can do is we can actually turn our indicator on, and if we close out of this window, we can see our rise time and how it's basically calculating it. And currently we're showing it's about a 2.4, 2.5 nanosecond rise time. So we know the problem's not coming from the rise time itself. So the next thing that we're going to do is we're first actually going to zoom out a little bit. And then what we're going to do is we're going to go into our display menu. And we're going to go turn on our color graded display to see if we can get any more information. And what we're starting to see is we've got an infrequent pulse here between our clock signals that we're not triggering on, but the embedded device itself is possibly triggering on, and that might be causing our communication issues. So in order to get more information about this, I can go and use our zone trigger, and I can draw it on. So let's just put it right here. And once we've got it turned on, we'll actually start triggering on our event. And we can really start seeing our trigger event. So let's move it over a little bit, and we'll see the zone trigger moves as well. And we'll change the scaling just so we can zoom in a little bit. And at this point, we can go into our cursor menu and then turn it on manually. And we can actually calculate a couple different aspects of this pulse, just so we can start looking for what might be causing it elsewhere. So we can calculate our amplitude by changing this. And we can start measuring all sorts of different aspects of this pulse itself, which allows us to then look at what might be causing it on the board. Timing is critical to any serial data system. Specifically for our embedded device, with debugging and analyzing the signal, monitoring the digital signal's timing is critical. To do this, I'm currently using the instrument's logic analyzer, and we're only looking at 8 of the channels. And what we can do with our logic analyzer, and what's unique to the 7000 series, is we've actually got the ability to group our different logic analyzer channels. And to do this, we can actually go into groupings and say group 0, 1, and 2 together. And then we can go back and we can turn on our group. And what this is nice is it allows us to highlight a couple of our different channels, or just group them together so we're looking at multiple buses or multiple digital channels of interest. Another nice feature is we can label our channels. And when we're labeling our channels, we can go into our library and say select clock to be D0, and once we turn it on, we'll actually see that we've got our label on the left-hand side of the screen. For actually monitoring the timing of our channels, we can go into our cursor menu, and once we're in there, we can go into manual, and then once we select our source to be the LA channel, we can use our digital cursors. And what this allows us to do is we've got 2 vertical axes, which allow us to look at the logic of each of, say right now, just our 8 channels, but all 16 channels in reference to the trigger point, which is our time 0. And what this allows us to do, say we move AX over, and we can get it to here, what we'll see is we've got our logic over associated with AX is all 0. And say if we move our BX point, and we can just pick another point, we can actually see the logic change. And this will actually represent with our channels themselves. And this is a great way to view timing at any fixed points in reference to your trigger, or just in timing in general. The key to any low-speed serial application is the ability to quickly and easily look at the data being transmitted. Ideally, the best means to do this is by having a decoded signal that you're viewing on your embedded device. To start off with, I've already set up the scope to be triggering on and then decoding a pretty basic SPI signal. And what we've got is we've got our trigger menu on the right-hand side of the screen, and then we've also got our decode bus in green here. And really what this is to show is we've got our SPI trigger set up, but we can also use a couple other triggers as well. So if we say go into the one-touch menu and we change from drag to draw, I can then set up a zone trigger. And with the zone trigger, I can set it up so it's only triggering on when the signal is either intersecting it, or I can turn it on so it's not intersecting. And this can be actually rather useful for excluding parts of your serial signal. Next, I'm going to show you a couple of the other advanced features of the decode menu. To do this, I'm first going to turn off our zone trigger. And then if I go into our decode menu, I've already set up our decode to be on decode 1. And we've got our SPI and everything. And then if I go into display, this is where you actually change your format on the decode bar itself, but I can also turn on the event table. And then if I were to scale out, start getting a little bit more decoded data, I can then also change the format on our event table to be the same as what we had on before. So let's go with ASCII. And then what we can see here on our event table is the actual packets going through, and then this time is actually correlated, so it's time off of our first trigger point. And we can go down and we can scroll through and see the data change. We can also then go into the event table and change over to the payload, which is another useful means of viewing the data, and it's actually rather effective for if you're looking at a long bit stream. You can easily look at a rather long bit stream and compare it to what you believe should be coming out of your serial device. Another way that we can view the serial data with the oscilloscope is by using the search function. And once we turn on the search menu, what we're seeing up here at the top of our screen is little white triangles along with a red one. And the white ones are basically indicating our different trigger points on the SPI bus, and the red ones indicating our current one that we're fixed at. And actually it's also highlighted on our marker table. And where this is valuable is, say, if we stop the instrument and we then select one, we'll move to it on the screen, and then if we use the marker table in conjunction with our zoom mode, we can then zoom in on the data so we can jump around on the signal. And this can be really useful for decoding a long bit stream. Embedded design and debugging of digital data is a growing test requirement in a broad range of consumer and industrial applications. Having the right oscilloscope can make viewing, analyzing, and resolving issues, including timing, signal quality, and data, easier and faster. This improves engineering efficiency and time to market. Regal's DS7000 series, powered by the dual-core Phoenix chipset and UltraVision 2, allow the instrument to easily perform all of your embedded testing needs. If you have any questions about this product or family of products, please contact us at Regal or visit regalna.com for more details.